In this video we're going to look at the Laplace transform of the unit step and also the idea of a region of convergence. Now we've seen the function here u of t before, that it's equal to 0 for t less than 0 and it's equal to 1 for t greater than or equal to 0, so this is our unit step function. Now in order to find the Laplace transform, we form the integral from 0 to infinity of the function. Well, the function here from 0 to infinity is just a height of 1, so it's just going to be 1 times e to the minus st by dt. So the integral we're interested in is from 0 to infinity of e to the minus st by dt. Now what we're interested in are the values of s, which ensures that this integral converges. Now what we mean by that is, if you remember back when we looked at this e to the minus st and we described this thing as a kernel, and we said that the value of t is a variable and the value for t is going to range off from 0 to infinity. So we're integrating here with respect to t, and you can see t takes on all those values from 0 to infinity. Now the value for s is a parameter, so we get to choose the value of s, and for each value of s we allow t to range. So really what we're interested in is this value of s. If you look at this little diagram here, well, s is a complex frequency. It's sigma plus I omega. So this is a complex plane. This is all our numbers sitting on a plane. The numbers don't just sit in a number line, they're actually in the complex plane. Now what we're interested in is finding the numbers here of s which ensure that whenever we work out the Laplace transform, so in effect you can say the Laplace transform would be the third axis here, so that would be our z-axis, and we want to make sure that that axis doesn't tend off to infinity. If it was to tend off to infinity, then we would say in mathematical speak that that integral diverges, okay? It doesn't converge. So we want to try and find the area here in this complex plane that ensures that this integral doesn't go off to infinity. So that's what we're really interested in, and that's what determines the region of convergence. So let's go ahead in the next slide and we'll see how to work out this region of convergence. So we want the values of s that ensure that this integral converges. Well, what is this factor here, e to the minus st? Well, we know that this s is sigma plus I omega, so that's e to the minus sigma plus I omega t, and when we split these two up, we get e to the minus sigma t plus e to the minus I omega t. Now, we know that this e to the minus I omega t, well, all that controls is the corkscrew effect here. Okay, so the complex exponential here, if it was for example e to the plus I omega t, then we could think that this corkscrew would rotate in one direction, and if it was e to the minus I omega t, it would rotate in the other direction. So the plus and minus in I omega t just determines the direction that all the phasors would rotate in. And also the value of omega would just determine how quickly they rotate. So it would determine how tight this corkscrew is, or how shallow or open it is. So this e to the I omega t doesn't have any effect on the height here of this function. So therefore it doesn't have any effect on the convergence. The only thing that has effect on the convergence is the factor e to the minus sigma t. So e to the minus sigma t has the effect of modulating this function or just changing it. So e to the minus sigma t could either make the corkscrew get bigger and bigger and bigger, or it could make the corkscrew get smaller and smaller and smaller. So the thing that controls the height on this effect, it controls the convergence, is this factor e to the minus sigma t. So in order to look at convergence, we must look at this function e to the minus sigma t. So we'll look at that in the next slide. So we've drawn out the function here, e to the minus sigma t and e to the positive sigma t. Okay, so you can see that e to the sigma t here, that's positive sigma t, as t tends off to infinity, that whole thing is going to tend towards infinity. So we've got that really written here. E to the minus sigma t, e to the plus sigma t tends to infinity as t tends to infinity. But the e to the minus sigma t, see that it's going to tend towards 0 as t tends to infinity, and that's what we've got written here. So e to the minus sigma t tends to 0 as t tends to infinity. So that's quite obvious from these two graphs what happens with this function. So now we're looking at the values of sigma, because those are the values we get to choose here. T is already fixed, I mean t is a variable, okay? So we get to choose the value of sigma. So if we choose a value for sigma would be greater than 0, then we would have e to the minus, and sigma would be positive t, which would be e to the minus sigma t. If sigma was less than 0, then we'd have e to the minus minus sigma t, which would be equal e to the sigma t. Okay, so we can see then that if we can find the region of convergence independent on the value of this sigma, whether it's greater than 0 or less than 0. So if sigma in this case here was less than 0, then we would have e to the plus sigma t, and that's going to diverge, okay, so there's no convergence. But if we had the value of sigma greater than 0, then we end up with the e to the minus sigma t, and you can see as t tends off to infinity, this one converges. So let's summarise that, and we'll finally have a little look and finish off this example. So the Laplace transform of our function is going to equal the integral from 0 to infinity of e to the minus st by dt. So when we do this integration, you get minus 1 upon s e to the minus st from 0 to infinity. Now we know that from the last slide that this is only going to converge whenever sigma is greater than 0. So it means that we could say that as t tends towards infinity here, we know that this value here, e to the minus st, will tend towards 0 whenever sigma is greater than 0, that is. So that's the extra proviso. We need to ensure that sigma is greater than 0. So the first part of that with infinity would give us a value of 0, and then it would be minus, and it would be put in a 0 for t, so n to the power 0 is just 1, so you just have minus 1 upon s, which is just the 1 upon s. So you can say that the Laplace transform of the function u of t, the step function, is going to equal 1 upon s, but we can't just write that, because we have to ensure that we write that it actually only converges whenever our sigma is greater than 0. So sigma is the real part of the complex frequency, so what we do is we write the real part of s, which is the sigma part, must be greater than 0. So this is the full Laplace transform here. U of t, Laplace transform is 1 upon s when the real part of s is greater than 0. And you can see that region of convergence here. We have our I omega, and we have our sigma, and the blue value here, blue line, shows that the region of convergence is whenever the value of sigma is greater than 0. If sigma was less than 0, this integral wouldn't converge, and you can see that drawn out a little diagrammatically as well. You can see that the corkscrew here is modulated by that envelope e to the minus sigma t. So as t tends off to infinity, this corkscrew tends towards 0. So we'll see that in the next few videos, and we'll see how we can adjust this region of convergence. Also note that I've got a little pink cross here. Now this little pink cross represents something that we call a pole. So if we think about the value of sigma and I omega tending towards the origin here, in effect tending towards 0, then we'll have 1 upon s, and s would obviously that would just tend towards 0, so we'd have 1 upon 0 which would tend towards infinity. So it means at that point there in the complex plane would tend off towards infinity, and we're interested in the position of these poles and also positions of zeros, which we'll look at over the next few videos. But that's all there is for this video. I hope it's been of use, and I'll get you on the next video. Goodbye.